Good afternoon, everybody. My name is Charlie Nicklin. I'm Chief Executive of IAgrE, and I'd like to thank you all for joining our July presentation. For today's lecture, I'd like to welcome Professor Kiran Tota-Maharaj from the Royal Agricultural University, who will be presenting on water resources and sustainability. Kiran is a chartered engineer, chair of the university's Water Resource Management and Infrastructure, and is a leading authority on water, energy, food ecosystems. As usual with our lectures, everybody will be muted. And if you'd like to ask questions, then please pop them in the chat at the bottom of your screen. And then at the end of the presentation, we can unmute you so you can ask in person. Okay, I'll now hand over to Kiran.
Thank you, Charlie. I'm just going to share my screen. Hopefully it works properly without any problems this afternoon. So thank you, colleagues from the Institution of Agricultural Engineers. A real pleasure to be here this afternoon virtually. Met a lot of colleagues at the IAgrE's annual awards, which was really, really rewarding to see the work that farmers are doing, as well as the prizes some of the students, both at undergrad and postgrad levels, receive from the Institution of Agri Engineers, IAgrE. My topic today is based on looking at wastewater reuse and capturing of wastewater. I'll go in some details. I'll be presenting a few case studies I've been working on for the last 3 years with Rural Ag and with my industrial partners, the WRC, the Water Research Center, based in Swindon, where I was a technical director for 3 years as well. So held these two positions, working side by side, and some wonderful collaboration with farmers in Gloucestershire and Wiltshire. So today's topic is looking at engineering circular biosystems infrastructure. When I use the word biosystems, I mean agricultural tech, the agricultural industry, the infrastructure related to the agricultural sectors, nature-based solutions for resilient on-farm wastewater reuse and capturing that runoff from farms, and how important it is when we look at water management, especially in the drought conditions. We are well aware of the cyclic behavior of the lack of rainfall versus the dry periods we're experiencing, and how that is becoming more and more difficult with the unpredictability of our precipitation levels today. And yeah, it's great to be here for this lunchtime lecture series with the key theme, water resources and sustainability. So when we talk about the WEFE, and now I think the Americans added an extra E to the water, energy, food. Now it's WEFE, so it's the water, energy, food ecosystems Nexus. And my approach has been, it is an integrated water resources management approach. So when I mean or talk about integrated water resources management, it means your water from flooding, from potable supply, from wastewater, it is all interconnected on any urban, suburban catchments. And the importance of wastewater, how do you look at wastewater management? And it is important to know that every drop counts in terms of wastewater across the world, should not be looked at as a waste product to be discarded. When we talk about wastewater challenges, at the moment, it's quite sad to report over 80% of wastewater exiting various sectors, whether it's domestic, commercial, and the industrial sectors, are being discharged untreated into the natural hydrosystems, your oceans, lakes, rivers, etc. So, but there's much more to be done when we talk about both centralized and decentralized wastewater capture. Looking at the potential of what can be reused from the biological, chemical, and thermal aspects when we talk about the heat energy, the thermal energy, and recapturing that with other technologies, which I'm happy to do a separate talk on that when we talk about heat pumps and water source heat pumps within wastewater treatment works. So 2.5 years ago, I joined the Royal Ag alongside my post with WRC, and I set up the Water, Energy and Environmental Engineering Research Cluster with postgraduate students and PhD students, specifically looking at how do we deal with your natural environments, runoff, capture, and the importance of your water, wastewater relationships for farms and the farming industry, how best we can look at it from a circular perspective, And a lot of times, that water is captured and it's conveyed or stored before lorries and trucks pump it away from your on-farm produced water on site. And when we talk about water resources for any agricultural sector and industry, how sustainable are these resources, And on the top right-hand part, you can see a GIF there on the precipitation levels, that unpredictability of rainfall. And a lot of folks may have seen examples where cloud seeding in countries like United Arab Emirates has failed completely. And there's a less than 5%, less than 3% chance of cloud seeding working at all, but yet still it's like probably 25 plus million US dollars pumped into the United Arab Emirates research and trying to drive cloud seeding to change the precipitation patterns. It's not working. So you have to look at more realistic ways of providing that water resource sustainably. And in terms of dealing with it, capturing it. Yes, rainwater harvesting is there, but what happens now when you have at least 2 weeks of non-precipitation levels? The reliability is questioned. Capturing that from other sources, so the wastewater coming from, yes, it will be varying levels of contamination. And for those who look at the very nice fun show, Clarkson Farm, you would see the farm wastewater has to achieve biological steps in terms of the total coliforms, the fecal coliforms, and the bacteria that must be removed, especially when it's feeding into your poultry farms as well as your dairy farms. And then there's grey water reuse as well, too, originating from other aspects, which can also be treated and reused for non-portable consumption and also further treatment for farm water supply. For example, going through detailed filtration and disinfection prior to reuse on farms. So what happens to the water used in farming and agriculture? Quite often, people don't realize that the agricultural sector uses 70% of fresh water resources globally. So in most countries in the UK, that's not the statistic. It's less than 30% from the fresh water supply that goes through to the agricultural sectors. But when you talk about Canada and the United States, it's closer to 70% of fresh water abstracted for the agricultural industries. And higher percentages from both groundwater abstraction and abstraction from your rivers and so on as well when you talk about India and China. So there is a challenge when we talk about the abstraction rates and the generation of agricultural wastewater runoff from the sector. So there's millions of hectares across the world using irrigated water in terms of land management. More than 60% of cultivated lands in certain sectors, and that's split between 40 and 60% used for agricultural produce versus vegetated produce. And when you look at the pie charts, consumption versus withdrawal, agriculture dominates in most countries, not so much in the UK, but globally, the agricultural sector dominates in terms of the abstraction rates of fresh water resources versus your consumption rates when compared to urban consumption, other industries, etc. So there's an agricultural water challenge for sure, 100%. And there must be a greater focus on wastewater treatment and wastewater capture for reuse purposes. And when you look at farms for poultry, dairy, and stables with the equine, large volumes of wastewater consist of nutrient-rich which can be reused in terms of capturing that phosphorus and nutrients as well too. And from a research aspects, there's more to be done when we talk about recovering these valuable resources from a water, food, energy perspective. And some of these challenges, yes, we are experiencing. Earlier this week on either ITV or BBC, one of the farms in Wales, the farm owner presented that the dairy farm dropped in production of milk by 1,000 liters, from 5,000 liters to 1,000 liters because of the drier conditions. The cows are not accustomed to that, so there's less consumption, but also the use of and the growth of hay and other vegetated goods and so on, it has reduced significantly. So there's a wider societal benefit when we talk about wastewater management and water reuse. And the technologies are improving. And some of the case studies I want to talk about in today's presentation is the use of microbial electrolysis cells and microbial fuel cells, which we are looking at alongside nature-based solutions in terms of treating that wastewater and on-site treatment and also creating bioenergy. So constructed wetlands have been around for a long time, also known as engineered wetlands or engineered hydrosystems. Using the natural vegetation, and it's important to not bring like foreign species and invasive species when you talk about vegetated and constructed wetlands. So there are a lot of native plants as well here in the UK and Ireland that looks at and have been looking at for a long time, for more than 40 plus years, the applications of surface flow wetlands and subsurface flow wetlands dealing with runoff, and especially agricultural runoff. So it does work, but it is there are negatives and positives towards constructed wetlands. And of course, one of the big drawbacks is the land use and land application when it comes to constructed wetlands on farmland. So one of the key focused areas from my water, energy, and environmental engineering research cluster at Royal Ag was looking at decentralized wastewater treatment systems. And in this photo and infographic, you can see a combination from whether it's a farm building and it's flowing through different stages for proper reuse. And the amount of reduction in your organic matter, it is in the high 80s to 90% when you have two stages of treatment, as shown on this infographic, combination of constructed wetlands, biofilters, and also anaerobic digestion systems in terms of the application. But of course, the cost is there, and the land use and land space is another question mark. But these technologies can work, and they reduce the amount of nutrients they entrap, pollutants within it, both organic and inorganic pollutants within the constructed wetlands and biofilters. And there's wonderful applications when you talk about both constructed wetlands, both in a vertical flow and horizontal flow mechanism. So you can see based on and a lot of the research that we're looking at is improving the sub-base materials, not looking at wasting or looking at virgin aggregate, but looking at more now biochar and chitosan, which is crushed seafood waste from your crabs and other seashells, grind it into a soil or media, to act as another filter media within your constructed wetlands or biofilters. So from lab scale to your agricultural fields, I've put a QR code from this research paper, which has supported us in terms of how do we look at developing and setting up nature-based solutions on site, capturing that direct runoff. So at lab scale and pilot scale, we've been looking at collecting wastewater. We have been collecting agricultural runoff and wastewater from 3 farms, including the Kemble Dairy Farm neighboring RAU, and 2 other farms in Wiltshire and Gloucestershire, a poultry farm and another dairy farm in close to Swindon. And how these systems are feeding various biofilters and constructed wetlands, looking at the plant type, looking at the sub-base material types, looking at the retention time and the flow rates as they feed into your pilot scale, lab scale, constructed wetlands and biofilters. So I'm now going to start a few of the projects that we are looking at, and we have been looking at with PhD students over the last 2.5 years. So Research Project 1, this project is in collaboration with University of the West Indies, St. Augustine campus in Trinidad and Tobago with one of my PhD students. And the project focuses on solar power irrigation systems and flowing the wastewater and also treated wastewater into a polishing stage of constructed wetlands. And then thereafter, research is looking at this treated wastewater, growing lettuce, kale, and watercress. So 3 sort of salad type vegetables and crops. So on the right-hand part, you can see the treatment works. That's the 3rd stage treatment works. And the left-hand part showing you a discharge point on site. And in the central picture is the location of the treatment plant in central Trinidad. So the PhD student is looking at a combination of treatment processes. So apologies for the sort of several lines and arrows in this diagram, but I'll try to go through it as easily as possible. So in the center part of the photo, it's a combination of different constructed wetlands. In terms of using organic geotextiles alongside gravel, pea gravel, and other planted wetlands. And the feed source is constructed wetlands from another constructed wetland into a second stage constructed wetland in the green arrow. The blue arrows, are showing you feed from the domestic treatment, wastewater treatment works. So it's going through 3 stages of treatment. And then at the effluent, rather than letting that water discharge into the river, even though it's meeting the environmental regulations for discharge purposes, it's capturing that water, the tertiary stage of treatment processes. So it's going through like sedimentation, filtration, a bit of disinfection, and again, we're capturing that water at the end of the wastewater treatment plant. And then the blue arrows are showing like a polishing stage. So you're adding further treatment to it, especially when it comes to growing the lettuce, kale, and watercress. And the student is completing that studies within the next few months in terms of the health and safety of consuming that water after more 4-stage, 5-stage treatment of domestic wastewater feeding into the constructed wetlands, and then using that water to look at aquaponics. So it's an aquaponic system in the center sort of light purple picture there. And then you can see it enlarging there. The center photo is it's the sort of 4-stage post-constructed wetland feeding the aquaponics. And then that aquaponic system is being used to grow the lettuce, kale, and watercress. So the photo to the left showing you the pilot scale constructed wetlands again, and that's post treatment from the domestic wastewater treatment plant. So it's more or less going through 4 stages of treatment before it reaches the aquaponics level in the PVC setup with the PVC pipelines in the center. And thereafter, the right-hand part of the photo is the environmental engineering lab at University of the West Indies, where the test is like, for BOD, COD, nitrates, nitrites, ammonia. So both physical, chemical, and biological water with wastewater analysis. So the project also looks at precision irrigation with drip irrigation to the system, and the water requirements for each vegetable crop, looking at per 1 hectare of agricultural land is around 70 meter cube of water per day per hectare. So an average irrigation flow is about 7 millimeters per day in terms of your rainfall measurement, with a lot of variations depending on the season type and crop type that you're looking to grow with these crops. The second research project with my next student is looking at the evaluating again of constructed wetlands here in the UK. And we've built up this project at Royal Ag with solar photovoltaics pumping air into the tertiary stages, so increasing the oxygen levels as the wastewater infiltrates and it goes through the treatment process. To increase the dissolved oxygen levels would increase the health of the water as well too. And looking at how can you use as a disinfectant to the end, for example, hydrogen peroxide, H2O2, as an eco-friendly treatment process. There's a company called Farm Water, which I've been talking to, where they've looked at the residual with hydrogen peroxide, H2O2. It does not have it does not leave back a chlorine residual in it. So you have to probably still look at chlorinating the water when it comes to feeding your horse stables, equine facilities, as well as your dairy farms, etc. And so the project to the left-hand corner, we built up a sort of mini greenhouse. And you can see to the bottom right-hand corner, the various pilot scales, constructed wetlands with varying the plant type, topsoil levels, using biochar in the middle sections of the constructed wetlands, and again gravel, pea gravel, to the latter stages of the constructed wetlands, the experimental rigs. We've looked at vet liver and cattail as some of the plant species for these constructed wetlands, and we've had sensors monitoring the total suspended solids, the total dissolved solids, pH, conductivity, as well as nitrates, nitrites within the effluent, and doing lab analysis on the biochemical oxygen demand, your BODs, and your chemical oxygen demand on the inflow and outflow of the rigs. One of the third projects looks at, again, constructed wetlands, and what we've embedded into these constructed wetlands, we've gotten wool, sheep wool from farms in the Cornwall region, and we've used the wool as an organic geotextile membrane. So it's sort of both separating, and as you know, some of you all will know, in terms of construction and preventing in landfill and so on as well, you have to have impermeable layers of geotextile. More inorganic materials and plastic-based materials are used for that. But when it comes to sort of the circularity aspects, we've looked at the potential of embedding wool as an organic geotextile membrane to increase the treatability of the wastewater as a single stage on-site process. And so far the results have been good, but this is sort of phase one. And then phase two, with the treated wastewater, we've had some kits with plasma activated water or POR, and looking at creation of the plasma activated water post-treatment of the constructed wetlands. And the POR increases the oxidation levels. It sort of creates an O3 ozone kind of configuration in the water. So the plasma activated water is quite good for germinating seeds. So you're using the wastewater, putting it through the constructed wetlands and biofilters, getting that right treatability, and then applying our POR system, and hopefully this video works. And that's showing you, so what this system is doing, it's generating, at small levels, you're just talking about 250 mLs of water, but it's creating that plasma activated water from the treated wastewater. And then that plasma activated water, we're going to use to germinate seeds and increase that levels. So it's sort of circularity from the wastewater, from the post capture of runoff from farms. The next fourth project is microbial fuel cells. Again, we're capturing wastewater runoff from farms, from both the poultry farms, the dairy farms, and the equine stables in around Wiltshire and Gloucestershire. We're feeding it into a microbial fuel cell. So the microbial fuel cell is a biobattery. And what it does, you have an anode-cathode relationship. So within the anode, under anaerobic conditions, so no oxygen introduced, and you have a separator called a proton exchange membrane or an ion exchange membrane. And what you're doing, you're creating a biobattery with your microbial fuel cell. So you're feeding it with wastewater to the anode, and you have a combination of, like, graphite used for the anode cathode, different metals, different materials can be used for the anode and the cathode. You are joining it up with copper wire or titanium wire to create that biobattery, and we are producing bioenergy or electricity. What the microbial fuel cell is doing is pushing the ions and cations across the proton exchange member or the ion exchange member to capture and create and draw your pollutants, your ions and cations across to create cleaner water. So within the microbial fuel cells, what we are looking at is the microbial metabolism, how good we are converting organic matter within the wastewater for bioelectricity or bioenergy. And these systems consist of, we are looking at how we can vary the anode and cathode. We can also look at using organic materials, even materials like sheep wool and other materials as your proton exchange membrane, separating the anode and cathode. And we are generating from these cells, feeding it with agricultural runoff, agricultural wastewater to the anode. We are generating energy in terms of between 5 to 10 volts based on the size of the biobatteries we have. So here you can see our sort of stacked fuel cells I've developed at lab scale. So what we can do, we can increase the volumes. So we're using the stack system by just increasing the volumes on the anode and the cathode side. We can also create a fuel cell or bio battery per cell. So you can have anode cathode. So it creates a combined system in series. So a lot of variations we can look at, or we have been looking at, monitoring the conductivity, pH, as well as the nitrates and nitrites behavior, both on the anode side and the cathode side. But the key importance is treatability of the wastewater and how much bioelectricity or bioenergy that can be produced from these microbial fuel cells from the research project number 4. And here you can see a schematic what is going on. Now you have microbial fuel cells and you have microbial electrolysis cells. So with electrolysis cells, it's the same setup, except you need to add additional power. So you have to add electricity. So it's a net abstraction from electricity. So again, utilizing solar photovoltaics, feeding it into your fuel cell. And the research we're looking at, the next phase is looking at waste plant materials and feeding those waste plant materials into the anode. And what you have here from the microbial electrolysis cells is as your system breaks down and fermentates with your sugars and acetic acids and so on as well, you have the breakdown and the generation of bioenergy through hydrogen. And I believe this is one of the fuels of the future. We have JCB, etc., using hydrogen engines for some of their tractors as well too. And I think when we talk about net carbon zero and achieving this and shifting away from diesel, oil and gas, etc., these type of technologies are futuristic and positive in terms of how best you can use agricultural waste products and generate hydrogen on site from it. The 5th and final project I'm presenting on is with another PhD student, and again, working well with supportive farmers on site. The combination of constructed wetlands with microbial fuel cells and as a low-cost on-site technology, looking at durable electrode materials for these systems. And what we have here, so phase 1, at the Royal Ag, we built up, myself and my student built up 6 rigs, and it was going through 3 stages of treatment. So constructed wetlands with bamboo. We started with bamboo first as a tropical plant, and then feeding through different stages. With the final effluent, we use solar-powered ultraviolet radiation, and that's us collecting on-site wastewater. So you can see the color and the high turbidity with the farm wastewater. And to the left, you're seeing the voltage. That's 0.94 volts measured across the constructed wetland with your microbial fuel cell. And this shows you the change of effluents across the inflow and the outflow conditions. So massive drop in turbidity, total suspended solids, as well as we achieved about 95 to 100% removal of BOD from the constructed wetlands. And this is, so I'll just go back one slide. So in terms of what we are seeing here, the treatability, you can see the cross-section on the right-hand slide, which I'll be sharing these slides to all members of IAgrE. So on the right-hand slide is the cross-section of our plants. So phase 1, we looked at bamboo, but feedback from the farmers, they said, well, we're not going to plant bamboo. It's an invasive species. So let's look at willow plants. So we have been looking at willow plants in phase 2. Wonderful results with the willow plant. Good growth, fantastic conditions. Using, willow plants and dwarf willow trees within the constructed wetlands. So when you look at the native species here across England and the UK, it's quite a practical solution for constructed wetlands and microbial fuel cell systems. So when we talk about the water quality, so 2 aspects again, water quality and your energy. So on site, we've had my meters, which includes color of the water with my color meter there, the HANA checker color meter, turbidity meters, pH meters, and the ion chromatography HAC spectrophotometer, which picked up nitrates, nitrites, phosphates, and ammonia. Alongside our water quality parameters to ensure we're getting the right removal and the right conditions for the World Health Organization, WHO, and other organizations when we talk about the standards for wastewater reuse. And it's been good results thus far. And we're also measuring, like I showed before, I'm just going back one slide. So 0.94 volts for earlier conditions, and that's our digital multimeter picking up the bioenergy across our combined constructed wetland microbial fuel cells. So that, in a nutshell, continued process from these cells can probably give you, in terms of layman terms, can give you enough charge to charge your phones or your smartphones within a couple of hours. So with our bio batteries, so it's across the constructed wetland, enough charge to charge your iPads or your iPhones. And some challenges with the combined constructed wetlands microbial fuel cells. Yes, we have clogging, and over time, that will reduce the amounts of total suspended solids flowing through. Again, excessive microbiological growth, especially in the hotter weather conditions with monitoring algae and so on. And the chemical aspects, the precipitation of salts and your metal hydroxides based on what type of water is flowing through and running off from your farms, especially when you talk about the applications of ammonia as fertilizers and that interaction with ammonia and other chemicals generating other byproducts within your agricultural wastewater runoff. And I think that's the end of my presentation. So I'm open to questions. I'm happy to share these slides with you. Thank you very much.
Okay, thank you for that. There's no questions in the chat. Can I just open the floor up if anybody wants to ask anything? Please speak up.
Just a question, Declan Flynn. You said about the clogging, and all the filters obviously have to do a lot of work. What's the kind of timeline on replacing filters? Is it competitive with normal water treatment?
Yes, thank you, Declan. Great question. And the expected time would be at least 15 years in terms of the life cycle of these filter media. But with like a conventional water treatment works, farmers themselves can apply, treated water from it and backwash and repressurize in an off-flow direction, because we've used gravity flow filters with it, especially with expected decentralized systems. You want to reduce that pumping costs to pump across the filters when you look at horizontal flows or upward flows. But when you talk about your on-site constructed wetlands and so on as well, depending on the configuration, if it's horizontal flow, Declan, you'd look at scraping off your sludges and putting the sludge to further treatment, and then thereafter landfill after every probably 10 to 15 years. For vertical flow constructed wetlands, again, backwashing through upward flow, pressurized, for example, treated water against the natural gravitational flow to clear up the spaces and pores between the filter media. And I think once it's maintained, that will give you additional 10 years of life cycle. But even with a bit of clogging, once the water flows through, once the pore spaces are okay, you will still achieve that desirable discharge. Compared to when you look at the Environment Agency monitoring discharge on farms, you will achieve a very high removal rate for the standards and the parameters that the EA in England would look at monitoring your farm discharge water quality.
Thank you. That's really good, and that's very, very uplifting as well. That there's this type of 15 years. It's fantastic. It's really good work you're doing. I'm really impressed about how you're going about this and how important it is.
Thank you very much. And I'm happy to share the slides because these are all my concepts that I've set up with the students. Massive support with my former CEO and president of, CEO and managing director of WRC, Water Research Center Limited. A lot of them have moved on now, but Andy Blackwell, he saw the vision of and full support in terms of, sitting in Swindon, historically WRC, always working with the wastewater utilities like your Thames Water, your Severn Trent, and so on as well. But it was a massive undertaking, and we were the few to look at the importance of like companies like WRC sitting with your neighboring partner institutions like Royal Ag, and the importance of finding solutions for the agricultural sector, because water is not going to go away from the agricultural industries here in the UK or internationally. And it's been real positive work. My students and I, we've been featured in a few of the local newspapers like the Gloucestershire Echo, and in terms of the research we've been doing. So, and the farmers have given us good support, and they've really enjoyed what we're doing. And like I said, simple examples of telling us, don't use bamboo. It's not going to be applicable to here in the UK. You guys can stick with that in the Caribbean, but you have to look at what works here in the UK and what the farmers would look at using. I think to add to this as well, when you look at the government, always changing of regulations in terms of the biodiversity on plants, and something I learned a lot from looking at Clarkson Farm, which I enjoy looking at Jeremy Clarkson making a fool of himself a lot, but I still learn a lot. Because when you look at the biodiversity on the farms, this ticks a huge box in terms of applications of nature-based solutions on farm using the native species of plants and your local soil materials, your local stones and rocks and so on as well. And it could be waste constructed materials from on site, feeding the sub-base of your biofilters, of your constructed wetlands, and achieving runoff on site. If there's challenges of space and challenges of land management and land use, yes, you would still achieve or want to achieve some treatability before storage. Because I think nowadays, to deal with the unpredictability, and whether you look at it as not so much the word it's climate change, but I would say hydrological change, because the hydrological cycle has been impacted by your combination of greenhouse gases, by your urbanization. And this is common sense that kids learn in primary schools with your hydrological cycle. So once you urbanize everything and you get rid of your plants and your grass areas, you're reconcreting it, you're changing your natural hydrological cycle. Where does your water flow? But in terms of the grassed areas, the farmlands, I think, in my opinion, the agricultural land applications, when it comes to crops and vegetables and so on as well, it's not altering the hydrological cycle. So I think it's other sectors that must take responsibility, especially the construction sector, in terms of the civil engineers looking at changing the hydrological cycle that impacts your precipitation, which is proven science. So I think, in my opinion, a lot more support should be looked at helping the farmers across the UK, and working with them. There are solutions coming out bit by bit, and of course the technology is changing with the use of drones, the use of automation, and I think with wastewater treatment on site, and even reusing that treatable wastewater would help that circularity tick box for farmers.
Okay, William, you have a question?
Okay, you want me to ask it? Okay.
Yeah, feel free.
Right, okay. You mentioned at the beginning of it using biochar, and I think it was crushed seashells and things,
yes,
as a filter medium. Obviously that will get to a state where it stops being effective because it's contaminated. What's your plan to do with that?
Meaning when the materials become contaminated.
When your filter stops, because your filter at some stage will be contaminated with heavy metals or other metals. Almost.
So the options would be backwashing, but when you backwash as well, so you would create that wastewater stream. So it's another, you'd have to put that through an additional treatment process, or even when you backwash the water to clean up the heavy metals and the organics and so on as well that comes through your chitosan and biochar. And you have to look at very good question, William, because you have to look at the physiochemistry and the biology behind it as well too. So there's a lot more research to be looked at from the chitosan and the biochar between the performance and even backwashing, what chemical constituents is there, what is happening to the water and what is happening to the materials. But then thereafter, the life cycle of these filters will come to an end. And the solution would be obviously to put it through some sort of process, whether it's, you know, some form of incineration or landfill, unfortunately, until you find that solution. Because when the pharmaceutical companies creates a chemical, the chemical, some of them doesn't magically disappear, yeah? It stays entrapped in terms of the filter media. So yes, you're removing microplastics and nanoplastics and heavy metals and so on as well, but certain things like, you know, these microplastics and phosphorus, it's not going to disappear. It's entrapped within the media itself. So your solutions is, yes, backwashing to clear it up, which will create that wastewater again, and somebody has to treat that wastewater. So I think very good question, because when you pump that water back from your treatment, it's not going to be possible to run it through your constructed wetlands. So the constructed wetlands are designed to take just your regular flow of your combination of mixed cow dung, you know, horse poo, etc., with water and feed from your stables, your dairy farms, etc., and your cow sheds and so on as well. But when you talk about the materials mixing it, the chemistry can become quite complex with time, and thereafter, in terms of the life cycle, you would have to replace the filters, I would say, after a 15-year period, including, you know, backwashing as well. And then when you create that backwashing and that runoff, you have to convey that to your wastewater treatment works. For example, have, you know, another lorry come pump it out. It's conveyed into a nearby storage tank, and it's taken away for treatment. But when you talk about wastewater reuse and so on as well, like you look at United Arab Emirates, where I went for a couple case studies and projects, they're looking at full wastewater reuse to water golf courses, and, you know, in 40 degrees Celsius with high evapotranspiration rates. So non-potable water reuse, it's something a lot of folks are looking at. When we talk about football fields, cricket pitches, golf courses, etc., yes, it can work, you know, in terms of feeding that for non-potable use. So I would say there's potential from taking that flushed backwashing wastewater from the filter media for non-potable use. And then when you look at the filter media reaching its life cycle, unfortunately, you would have to dismantle and remove the filter media at the end of 15 years, and then look at sending it to a landfill.
Yep. Thank you.
Yeah. Thanks.
Okay, Tim Reynolds.
Oh, great presentation. Thank you. I got from your last slide, you were suggesting that actually mobile phones can be charged from the cells being generated. How are you actually capturing those currents with sort of copper meshes within the cell, or
so we have multimeters connected to it. So it's basically when you look at let me get a better photo. So when you look at the cross section, right?
Yeah.
Of the top right hand part, you have a graphite plate sort of separating the top subbase of your garden soils and so on as well, and another graphite plate in the base, in sort of that dark maroon color. Within the graphite plate, wires are connected like it's an anode cathode.
Yeah.
So it's joined across, and you have your resistor across it. So you created a battery.
Yeah. Yeah.
And from that battery, you can feed from the voltage and current generated, you can feed it in terms of charging of a phone.
So how much power on, for example, 100 square meter cell, how much could you actually recover? How much energy would be recovered from that?
Oh, you're asking me a tough mathematical question. Let me think now. So, well, what was quite unique from our measurements, that what we found, that the increase of the organic matter, meaning how concentrated the COD and the BOD is, we weren't seeing a significant difference in that voltage. You know, in terms of varying it. So the highest voltage we got was about 9.8 to under 10 volts. Yeah. So with each constructed wetland. So when you look at it, it's the central picture there. It's probably about 180 centimeters in height, each constructed wetland. And we won't, when we increased the concentration and we saw the higher load coming from the farm, because all of these cells are using real wastewater, so we're not altering anything. We're just collecting that real farm wastewater. We're pumping it, and we've not noticed with a higher organic load and increase in voltage or current.
Okay, yeah.
So when you ask that right question, if you increase the cross-sectional area of the constructed wetland hybridized microbiofuel cell, would it increase the voltage? From our research, Tim, so far, the answer is no.
Yeah. Okay.
So if we're just getting that under 10 volts for this system showing here, based on heavy organic flow from your farm runoff, I would think that, you know, the expected bioenergy or bioelectricity would not be directly correlated to the size or the cross-sectional area of the cell.
Okay.
But it could be other factors that we have not looked into the research, or we probably still have to dig deeper, meaning plant type, hydraulic retention rates, and what materials we use, Tim, between the anode and cathode. Because yes, we're testing graphite because, you know, easily available and, you know, for pilot scale for research purposes. Obviously, certain metals and certain other anode cathode materials we can't look at based on cost and application. I don't expect me convincing a farmer, you know, place some titanium plates or, you know, expensive metals, you know, between an anode and cathode. But I think this is where the research comes by, but you could look at other organic loads. For example, a lot of people across the world are looking at biochar as an anode material and a cathode material. So our phase 2 of this project, if I go to the microbiofuel cell one, where if I just go back a couple cells here, and I show you this one, we are using in phase 2 of this microbiofuel cells project biochar and activated carbon in the anode cathode. What we found that we had to create a little cage or a little netting, like a tea bag, you know, and filling it in, but then we had challenges of corrosion and so on as well based on the type of materials we use in the anode and cathode. But if we can use organic materials as an anode and cathode, it's a win-win. Rather than try, and then of course you would be well aware of that biochar coming from different sources as a waste product as well too. So there are research going on to say, can we use organic waste products as an anode and cathode to embed a further circularity into the microbiofuel cell system?
Cheers, thank you.
You're welcome.
Okay, question from myself. I saw a project maybe 3 or 4 years ago in South Wales on a farm where they were taking slurry, extracting the solid matter, and then treating that water to a point where it could be refed to livestock.
Yes.
So not just waste, you know, actually cleaning it and rehydrating cattle with it. Do you know if anybody's doing that commercially yet, or is that still sort of research?
This company that they brought me in touch with is called Farm Water, and I've been exchanging some comments with them on LinkedIn in terms of so Farm Water is disinfecting the water. I think the chap is a veterinary doctor based in Southwest, either Cornwall or somewhere in the Southwest. And he runs this company called Farm Water, and they're looking at the treatability and using. So he has used from a partner company called Gaffey, and I'm happy to share those contacts because they saw the importance of the combination of hydrogen peroxide H2O2, disinfecting and oxidizing the water for the cattle, for the cows and the animals to consume, right? And then he's still applying chlorine dioxide as the disinfectant. And why he has stated that for is because with H2O2, with the putting it through the filtration system and then of course disinfecting it, it's not safe because the biofilm is still reappearing post hydrogen peroxide disinfection. I like the fact of using hydrogen peroxide H2O2 because from a chemistry point of view, you are dealing with H2O2. So the combination of the hydrogen and oxygen molecules splitting and generating, you're talking about if it mixes, it will reform back into water molecules or separate back into oxygen and hydrogen molecules versus chlorine. But I think from a water perspective, Charlie, we cannot get away from the use of chlorine, even for on-farm use, for disinfecting the water, safe for cattle, goats, sheep water consumption, and your equine stable and horse stable farms and so on as well, your horse facilities, for all of these animals for consumption, safe water consumption for farm water, you have to still go put it through. I would say use of constructed wetlands will help it achieve great treatability, but prior to the animals consuming it, you have to disinfect it. So disinfection is a must post constructed wetlands.
Okay, thank you very much. I don't think there's any more questions. Declan, your question, they'll be available on the IAgrE website, the slides at some point, along with this.
I'll be emailing the slides in 5 minutes.
So Sarah will put them on the website at some point. Yeah, so if there's no more questions from anybody, I'll draw things to a close. So thank you, Kiran, for a really interesting presentation and taking the time out to do that for us. It is appreciated. And thank you, everybody, for joining. And I hope you join us for our next lecture, which is on the 11th of August. And we'll have Dr. Marcello Prikop from Harper Adams University, who's going to be presenting on the use of simulation in ag engineering. Additionally, it's worth saying at the end of this month, we have an evening lecture on the 28th of July, and that's at 7 p.m, where we have IAgrE member Ray King, who will be talking about the role of startups and how they the part they play in our sector. So thank you very much, everybody, and we'll see you next time. Bye-bye.